As I said, I'm going to make you kind of go through something like this with a few more observations on basically a similar system, except I think I'm going to ask you for one in which k is equal to 2, but the logic is all exactly the same. And there are some more examples in the reading. So again, be sure to be just clear on what that's about. And again, the idea is you want to strictly follow an algorithm here. The importance of that, again, is that if you can strictly follow an algorithm without having to do much thinking, then you stand a fighting chance of being able to implement it on the computer. If you have to do a lot of thinking, meaning higher mental processing, and we'll kind of see an example of this in what we're going to talk about today. If you have to do a lot of higher cognitive processing, then there is almost no chance of being implementing that on the computer. And I don't care what the AI guys say. I mean, we're talking about real intelligence, not the artificial kind, except no substitutes. Okay, so let's continue. So one of the main reasons why we do this is because not for its own sake, but because we want to find something out about the system. And so to that end, we will use some basic statistics. So you hopefully have not thrown away your stats notes. We are first I'm going to talk about types of averages, because in simulation, it turns out that there are two kinds of averages that we look at. One is actually called a tally, which is the standard average that you know about, which is adding something up and dividing by the number. But there's another more important one that comes up, especially in the model that we're looking at, and that is a time varying average. If we were to ask the question, for the model that we just ran, what was the average number in the queue? Or what was the average number in the system? Then we can't just add up the observations and divide by the number. That should be fairly obvious, but if it isn't, just hang on and that should be made clear. The tally, it turns out for the model that we have, in order to estimate the tally measures that we would be interested in, we actually have to do some higher order processing, which means that we're not going to be able to do that on the computer. But there is something called Little's formula that kind of saves our keister in that regard. So we'll see what that's about. Okay, the two averages. Tally, this is what you learned in your stats class and have probably known about for, since kindergarten or something. With a tally, if you have discrete observations, then, and I want to say, what is the average? Then I add them up and I divide them by the number. Now that, of course, assumes that they all have equal weight. There's a thing called weighted averages that you probably learned about in your stats class. Again, we're not going to worry about that here so much, but in a way that kind of comes into play for the time varying values. So in a time varying value, we have continuous observations, and there the average is computed by the area under the curve divided by the time. The area under the curve divided by how long we're actually doing it. That's how we do a time varying average. And what that does is that basically weights all of our observations by the correct amount. And we'll hopefully see what that's about. Okay, so now here's our hand simulation results. So what we just did and kind of cutting out all of the event list stuff, which we're not interested in anymore. All the event list stuff was just to make sure that our system was acting correctly, and all it basically did was kind of produce these state trajectories. So if we look at Q, if we look at the values of Q, then we see that Q has a state trajectory if we match it with the times. And likewise, the value of S, the number of available servers, it has a state trajectory that if we match it with the times, gives us that state trajectory, and also for L. In fact, we can graph them, and the graph would look something like this. These are the three state trajectories for what we just did. The number in the queue, okay, so it starts at 0. Then remember that it kind of popped up and then immediately back down. And then it went up and it stayed there for a little while and then finally came back down. Similarly, for the number of available servers, it started at 1, but then it kind of bopped down, and then it bopped up and down again, and then et cetera.
Arnie, with that, what is the width of X when it just goes straight up and down at the same time? Is that 0? So we're calling that, so
yeah,
basically
0.
it doesn't,
Yeah,
so it won't change. Okay.
Yeah, if you just have a spike, it's the base is 0. So now these are state trajectories for a little bit longer run. I think we ended ours right here. And that would be kind of here. And then likewise about here. Okay, these numbers aren't exactly matching, but that's okay. Yeah, I think you get the idea. So if I want to know the average number in the queue, then what I want to do is I want to compute the area under this. So if I wanted to compute that at time when did we end? We ended at time 5. Well, arrival, start service, end service, start service, 5.6. So at 5.6, at time 5.6, which is where we are here, I want the area under the curve divided by time 5.6. So whatever this area is. And likewise, for the number of available servers, I want the area under the curve divided by 5.6. And for the number in the system, now remember the number in the system was a little more complicated. So it kind of, but we still want the area under the curve divided by the time that we're looking at it for. Now, the thing is that for this, we actually can apply an algorithm. That is, if we're looking at the whole thing, then we would have to do a lot of thinking. But it turns out we don't have to do a lot of thinking. And we'll see what that's about. So if I'm looking to find the averages, the time average, the averages of Q, S, and L, well, first of all, to note that the tally average is not correct. In other words, I can't just say, okay, well, I had Q is 0 here. It was kind of 1, but then 0 again, and then it was 1 again, and then it was 0. So that would be 1, 2, 3, 4, 5, 6. And so I can't just sort of add them and divide. That shouldn't make intuitive sense. And certainly for L, if we look at this, I have 0, and then 1, and then 2, and then 1 again, and then 0. So that would be, 0, 1, 2, 1, 0. I can't just add these up and divide by 5. That really doesn't make any sense. I need to account for the time spent in each state. In other words, you see, the time that I spent in state 2 here was much less than the time I spent in state 1 or even state 0. And so I need to take that into account. Again, time average is the area under the curve, actually over time, divided by time. Now, if I'm looking, again, if I'm looking at this whole graph, I've got to sort of sit here and slice things up and figure out what that various area is. But it turns out that we can compute the time average as each event occurs and keep a running total of the area under the curve. So the idea is that we can update at each event, we can update our running total area by the previous state times the time since the last event. In other words, you can add that in every time. So let's take a look at how that, well, the formulas, which I decided to give in these scary calculus ones, are, again, the average number in the Q would be the value of Q over time, integrated, remember the integral is the area under the curve divided by time. Similarly for the servers and the average number in the system. And we can put a hat on it because that's how you do statistics. You just kind of put a hat on something. Now, the tally averages we would be interested in, though, are things like the average time in the queue. So on the one, I might be interested in what's the average number in the queue, but I would also be interested in how much time on average did my customers spend in the queue, because that's going to be kind of a function of their happiness or unhappiness. Raise your hand if you love waiting in the queue. Okay, I'm not seeing any hands, but so so this is a measure that we would be interested in, and that's a normal tally, because if we have n customers, each of them would have a certain time they spent in the queue, and our average would be just the normal average of that. And likewise, there would be how much time they spent in the system altogether. That's the time from when they showed up to when the time they left. And each customer would have one of those. And so if I wanted the average, again, I would simply add them up and divide by the number. Okay, so let's look at the time varying averages for this. So now I've given, in this, I've given the whole shebang, as it were. But let's just try to look at this piece at a time. So in fact, what I would like to do instead is just to emphasize this. Let's see if we can do this on the whiteboard. Okay, I might have to switch back and forth, but okay. So let's just look at L. Okay, so here we had time and the value of L, and then what I want to keep track of is the integral of L of t dt. That's the area. So at time 0, the value of L was 0, and we're going to always initialize at 0. So that's something that we're always going to be doing. Now at time 2.1, we had an arrival and the value of L went to 0. And now I want to update this. So how do I update it? Now again, you can kind of look at the graph, but the problem with looking at the graph is that the computer doesn't kind of know from graphs. I can't hold the graph up to the monitor and have the computer understand it. I need to be able to do it algebraically. Okay, so how do I update this? Well, I take my old value, which is 0.0, and I add in my old state, the previous state, times the elapsed time. And what's the elapsed time? The time between now and the previous state change. So this would be 2.1 minus 0. Okay, so 0 times 2.1 minus 0 is 0. Okay, then at 2.1, I had another event. The value of L was still 1. But again, I want to just mindlessly do this. And so I take my previous value plus my previous state, which in this case is 1, times the elapsed time, which is 2.1 minus 2.1. Again, I'm just kind of doing this blindly. And so my increment here is just going to be 0 again. So now again, I'm doing a lot of work here and not making a whole lot of progress. But the thing is that for the computer, this is like done in milliseconds. So it's no problem for the computer. It may be a problem for me, but get rid of some of this detritus. All right. All right. So now let's look at the next one. The next event was at time 3.5. And there, the value of L went to 2. So again, I just blindly apply my algorithm, which is take the old value and add in the old state times the elapsed time. What's the elapsed time? 3.5 minus 2.1. And now we got something. So that is 1.4. The next event was an end service at time 4.3. Then the value of L went to 1. Okay, now this is now things are a little more non-trivial. Our old value was 1.4. And now we want to add the previous state of 2 times the elapsed time, which is 4.3 minus 3.5. Okay, so that is, last I checked, that is what, 0.8? And 2 times 0.8 is 1.6. And 1.6 plus 1.4 is 3.0. Okay, do you see how that goes? So I think we can kind of stop this here. And let's come back. Okay. And basically, so what I did there was I just produced this amount. And by following the same process, you can do the same thing. I mean, so I'm not going to take it to its completion. Now the average here, this value is 4.3 divided by 0.3 divided by 5.6 approximately. I actually like to kind of keep them in this form because this is exact, this is approximate, but okay, and you apply exactly the same rule for all of these. And it may, again, like for a lot of these, it may seem like you're spinning your wheels, but again, on the computer, that's not a big deal. Now, there's one measure that is very useful, and that's called utilization. And for these kinds of systems, we are often interested in, how much time do our our servers, how much time are they busy? Because I mean, if I'm the bank manager and these are my tellers, then they get paid regardless of whether they have any work to do. And if you're a teller, the work is serving the customers. So if I have tellers and if my average utilization is like 20%, that means like 80% of the time I'm paying people to sort of sit around and update their Twitter feed. Okay, that's not cool. On the other hand, if utilization is really, really high, then that's not so good either, because that's correlated with high queuing times. Okay, but nevertheless, I can still compute the average percent of the time that the servers are busy per server by this formula here. Again, I got this scary integral that as we saw, we don't need to use high calculus for. The most we ever need is to compute the area of a rectangle, which I think most of us can do. And so since this was the number of available servers and we want the busy servers, we just take 1 minus if we divide by the number of servers, that's the average number of available servers per server. And 1 minus is the average percent of the time that the servers were busy. So in our example, this was 2.1 over 5.6 as the average number of available servers. And so 2.1 was the area. That was the area. 5.6 is the time. K was equal to 1. Take 1 minus that, and then we get this value. So we can, and again, we only have a few observations here, so this isn't a number we can take home to the bank, but this is how you could compute this. Okay, so now, what about the delays in the queue and the time in the system? So let's take a look at that. So here's the problem. The problem is let's look at the delay in the queue for our first customer. We can kind of see it from here. Our first delay was 0 because they showed up, they started service right away. The next one was the second server, the second customer had a delay of 0.8 because they showed up at time 3.5 and then they didn't start until time 4.3. And notice they had to kind of wait until this end service event occurred. So again, the first customer shows up at time 2.1. They get served at time 2.1, so their delay is 0. And if we want their time in the system, they ended service at time 4.3, and so they spent this much time in the system. The second guy, remember, showed up at time 3.5. They started service at time 4.3, and so their delay in the queue was 0.8. And their end service time was 5.6. And so their time in the system was 5.6 minus 3.5, which was 2.1. Last I checked. I think the arithmetic is correct on this. Okay, but again, this is important. Notice that what we had to do is we had to look at the entire run here and then sort of pick out these events. And for a more complicated system, for a longer system, we would have to do even more of this. And as I hope you can see, this is not something which we can easily do. In other words, we have to do a lot of higher processing, not super higher processing, not rocket science, but we still have to do a lot of thinking. We have to look at this and say, okay, he showed up here and then he left here, and that was that guy. And then sometimes they get mixed up. So in other words, sometimes it's particularly if we have more than one server, somebody can kind of come in and leave while the previous person is still waiting. Okay. But doing it by hand and kind of just looking at these small numbers of values, we can figure this out. And so if we wanted to do the tally statistics for our delay in the queue and our time in the system, again, so here are our observations. Now this is like that, remember that, that statistics calculator that we did last quarter in Java? We can basically do something like that. So, so we have 0, 0. And then for the first guy, we have a 0, and then the second guy, we have 0.8. The first guy getting the time in the system is 2.2. Then the second was 2.1, and the sum of that is 4.3. And so the average delay in the queue for this would be 0.4. And the average time in the system would be 2.5. These are two statistics that we can get by examination of the entire run. And we pretty much have to do it by hand. So it turns out that when we implement this particular model on the computer, we're not going to be able to exactly extract these values, because if I run this for 1 million customers, I'm not going to be able to sit there and pick out which ones came in and when did they leave and get service, et cetera. And that's not a reasonable thing to do. And the model isn't really set, this particular model is not set up to be able to directly estimate these. However, there is a saving a saving principle called Little's formula. And Little's formula basically says that if we want it relates the average number in the system, the average time in the system, to something called the average arrival rate to the system. So if I know 2 of these values, I can get the third. So the relationship is exactly this. L is equal to lambda times W. So if L is the average number in the system, if W is the average time in the system, and lambda is the average arrival rate to the system, then it turns out that when the system is empty, then this exactly holds. And it doesn't matter what the system is. It doesn't matter what those arrival times and service times were. It simply doesn't matter. This actually is always true. I could show it to you mathematically, but for right now, for our purposes, we're just going to have to kind of believe it. I'm going to demonstrate it rather than try to prove it. Now, as I said, when the system is empty, then it exactly holds. Well, what about if it doesn't hold? Well, for small numbers, if we only run the system for a short period of time, then yeah, there can be big differences. But here's the thing about a system like this, these queuing systems, and there are a bazillion queuing systems, and we're just looking at the simplest one. And it turns out that you can show that with a system like that, there are only 2 possibilities, and smart statisticians have proved this, much smarter than me, so I'm not going to even try. But they have shown that either the system will periodically empty out, that is, periodically it's going to be empty, or the system's going to blow up. And what that means is that, at least theoretically, eventually the queue is just going to grow to infinity. And it turns out under very, very mild assumptions, and what those assumptions are, we don't have to concern ourselves with. But for any system that does not blow up, then Little's formula, again, it holds exactly when the system is empty. If we start it empty, that's kind of the other caveat. If we start the system empty, then Little's formula is going to exactly hold when the system is empty. It's going to hold approximately and asymptotically as t approaches infinity. In other words, if we run our system long enough, then it will approximately hold. Now, after we have a few models under our belt, we're actually going to be able to demonstrate this. But for right now, we can actually prove the first part of it, or at least not prove, but demonstrate. So the demonstrate is a little bit different than prove. Okay, so let's take a look at what Little formula looks like in our example. Remember, I mentioned the arrival rate. So what is the arrival rate in a system like this? It's the number. If we wanted to try to estimate it, we would simply count the number of arrivals and divide by time. In the example that we had, we ran our system for 5.6 time units, and in that time there were 2 arrivals. Remember that? So lambda, our arrival rate, is 2 over 5.6. Now remember, I'm going back to fractions rather than decimals, just to show how exact this is. Okay, this we computed. L at the end, the area under the curve was 4.3. It was time 5.6. We also computed this 4.3 over 2, back a couple slides. See, remember the average time in the system, 4.3 over 2. Again, so rather than doing it decimal, I'm going to do it as a fraction. And our arrival rate, which we did up here, is 2 over 5.6. Now look what happens. The 2's cancel out. We get 4.3 over 5.6. So our lambda times W is exactly equal to L. Similarly, remember, so Q, our average number in the Q, was 0.8 over 2. Again, lambda here is still the same, 2 over 5.6. And I'm sorry, yeah. Our average number in our average delay in the queue is 0.8 over 2. Our average number in the queue, remember, it was 0.8 over 5.6. Again, approximately 0.14, but I want to keep it as a fraction just to show how exact this is. See, this is exact. Okay, so the average, this is the average number in the queue, 0.8 over 5.6. Here's our lambda. Here's our average delay in the queue. And again, let's see, let me change colors. The 2's cancel. And we get exactly 0.8 over 5.6, which is what we had over here. Now, again, this doesn't prove anything. However, it should give you some pause. It should suggest to you that even though this may seem like a kind of strange relationship, that in this particular case, it actually held exactly. And now you may be thinking, well, okay, the instructor is a sneaky guy. He probably jury-rigged the numbers so that they would come out. And that could very well be the case, because I am a sneaky guy. However, this is something which actually holds. And it's something which in the assignment, I'm going to ask you to kind of demonstrate for another set of values with a few more observations. Okay, so now let's look at exactly the same system with just one little difference. What if we had two servers? And again, I'm not going to torture you by kind of going through it by hand as I did before, but let's just take a look at this. So again, we always start. Okay, what I'm going to do is I'm going to take exactly the same system that we had and said, well, what would happen if we added another server? That's the kind of thing that's the kind of what if analysis that we can do with these models, because it's much easier and cheaper to add a server to a simulation model and say, oh, okay, now what's going to happen, than it is to actually hire another server. So the numbers are all the same, the service times, the arrival times, etc. So let's take a look at how we would do that by hand. And this is, again, something I'm going to be asking you to do. We always start exactly the same. In other words, the time and the current event and the states are all undefined until we define them. And the only thing is, and the run event on the event list at time 0. This is how every single simulation will start. This is how every simulation on the computer will start. It will start with the run event on the event list at time 0. The logic is always exactly the same. We take the next event, we advance time to it. Okay, in this case, 0 to 0, nothing to 0. The run event, we initialize Q to 0. Remember, the state transition for run was we set Q is equal to K. K in this case is 2, so now S is equal to 2. L is still computed the same. So remember, L is Q plus S plus K minus S. Okay, so Q is 0, K is 2, S is 2, so L is 0. That works. We schedule the first arrival. That was the same as what we had before. Again, we turn the crank. We have an arrival. All it does is it adds 1 to the queue. So the value of Q is 1. S is still 2 because the arrival event doesn't change S. L is now 1. And if we plug Q and S into this formula, that's what we get. Now we have a start service at time 2.1 and an arrival at time 3.5, exactly as we had before. And likewise here, we have a start service at time 2.1. Now, what does it do? It takes one guy out of the queue. So Q goes from 1 to 0. And now S goes from 2 to 1. Okay, so now, again, we just kind of keep turning the crank. Start service. Start service. We take Q goes from 1 to 0. S goes from 2 to 1 now. Come on. All right, so up to now, everything has been the same, but now look at what happens with this arrival. So again, the arrival is the next one to happen. Arrival simply increases Q by 1. So now we have 1, 1, and 2. But now, remember, what's the criterion? The criterion was S bigger than 1. So if S is bigger than 1, we schedule a start service immediately. So here's where the difference is. And then notice that we now have 3 events on the event list. You may have thought before, well, here we had 1 event, here we had 2 events, but we can't have 3 events. Well, of course we can have 3 events. Okay, and all arrival does is perform its state transition, which is to increase Q by 1. And then schedule, in this case, it can schedule the start service because this is, S is bigger than 0 is true. S is bigger than 1 is actually false, but S bigger than 0 is true. So we schedule this start service. And now this is where things start to differ from the previous model. And so now that start service is the next thing to happen. All it does is it performs the state transition of decreasing Q by 1, decreasing S by 1. and then scheduling an end service. Now the end service, the time was 1.3 was the service time. And so now we have the end service from before. This is the new end service. Again, here we added the arrival in this particular case. Okay, but now the end service happens here. Q is 0 now, so end service isn't going to schedule the start service. And then at time 4.8, we have another end service. Q is still 0, so we don't schedule anything more. In this case, we left the arrival on the event list, but we've had our 2 service completions, and so now we're complete. And so now our couple things to notice. First of all, notice that we ended 0.8 time units earlier. So, and our state trajectories are going to be slightly different. In fact, our state trajectories for Q, there's the average number in the queue is actually 0 in this particular case. But the average number of available servers is going to be, notice it's going to be weighted by the 2 and the 1 here by the times. And likewise, the number in the system is going to be different. And if we look at this, you will see that our measures here, as in this tiny little example, have all improved. And in general, that's always going to be the case. In other words, for a system like this, if I want to do better, there are basically I only have 2 options. I can add servers, or I can make them work faster. So faster would mean that these service times, if I could somehow decrease them, then I could keep the same number of servers. Or if I wanted to, if I wasn't willing to do that, I could hire more servers. But basically for a system like that, those are pretty much the only 2 possibilities that you have. And that gets into things like, okay, how could I increase the speed of my servers? It might be through training, depending on what their task is, it might be through training. Sometimes my quote servers are actually machines. And so if my servers are machines, like for example, like in a metal shop, I've drill presses and lathes and maybe some automatic machines, and I might have some 3D printers and other types of stuff. If I want to improve those, I can do an upgrade. I can, by souping up the machines, make them go faster, or I might have to buy faster machines. If my server is like a 3D printer, and I'm not getting the kind of measures that I want, I might have to buy a faster 3D printers or faster drill press, or this is a thing. Or I might say, well, I'll just buy some more, buy more of the slower ones. And in fact, that's a trade-off that we sometimes have to make. In other words, do you want to get the latest and greatest, or is it enough to just buy more of the oldest and least? Those are the kinds of things that simulation models like this can answer. In other words, here, just with this tiny example, I hope you can get a sense that we could address the question, if we wanted to improve our performance, could we do, how much performance could we improve by adding more servers? We could answer something like that with a model like this. Now, obviously, if we're only looking at 2 customers here, that's just woefully incomplete for doing anything in terms of definite conclusions. However, once we get this on a computer, we can run the bejesus out of it and then do some analysis on it. That's something that we're going to start to do toward the end of the week. On Thursday, we're going to actually put this on the computer. But first, there's something called event graphs that really we're trying to move to. So here's a critique of what we've just done. Here's a critique of the description of the multiple server queue. And that is that it is, first of all, it's verbose. You know, there's a lot of words in there. And words like that can be challenging to see what's going on. So more importantly than the verbosity is that it doesn't really show what the structure, it doesn't show the relationship between these different events. That relationship between those events is kind of is a critical element of looking at one of these systems and seeing how it operates. And so that's what we're going to be doing next, something called event graph methodology. And that's going to be our main language moving forward for describing these models. So instead of all this verbiage, we're going to be able to draw a picture. And that picture is going to be worth easily 1,000 words or more. And we need to learn how to do that. And that's what we're going to learn how to do tomorrow. And that's what we're going to learn about if you read section 3. Okay, the question, do assignment by hand or in Excel charts and calculate this word? I will accept however you want to do it, whatever you need to do to make sure that your calculations are accurate. I will accept doing it by hand as long as it's done neatly. If you want to do it in a Word document to make it look nice, that's fine. There's no extra credit for that. If you want to verify your calculations on a spreadsheet, that's fine too. I mean, spreadsheets are a terrible tool for doing this kind of simulation. They can be a good tool for doing these kinds of calculations. You have to be a little bit careful though. So if you're a whiz at Excel, or even if you're moderately okay with Excel, that's fine. But the key is to really, what I want you to, my purpose for torturing you like this is for you to get a sense of what the computer is doing. Because when you're debugging a model, the challenge with debugging a model like this, as opposed to just a plain old Java model, as we've seen with the Java models, we didn't delve into it too deeply, but it has this debugger where we can go step through the code. The problem with this, with simulation models like this, is that stepping through the code, while it's useful for some things, doesn't really tell the picture. What we want to know is when we have implemented our model on the computer and we start running it, the questions are, I mean, it basically boils down to this. Does every event perform the correct state transition? And how do we know? And does every event schedule the right events and maybe not schedule the events that it shouldn't? And how do we know? For that, the way we would know is to look at the event list. Like if you looked at that tableau, after every one, I had the event list. And after every event, I could look at that event list and say, okay, is that what I expect? Is that the right thing? Now, the problem is the debugger isn't going to tell you that. We're going to need to kind of look at some more things. Again, it's not that the debugger is very useful, and the debugger can be useful for certain things in this, but we're going to need to basically run our models on the computer and have it spit out pretty much the same information that we're doing by hand here. Fortunately, there is a way to do that, and we will see that. But again, to make a short story long, when it comes to doing the purpose of kind of doing it by hand is partly so that you really have a sense of what is going on with these events. And second, to sort of get an appreciation of the fact that we can do it on the computer. So in other words, when debugging a model and you're looking at it event by event, you want to be forming a hypothesis. That is, when this event occurs under this state, then what events would I expect to see on the event list and at what times? So you need to be able to have that in order to say, well, is what I'm seeing the right thing? Is the model behaving correctly? And if I don't have a sense of how the event list actually works, then I may look at something and say, yeah, that kind of looks okay. But if I looked at it more carefully, then I would say, well, there's a problem here. Okay, so that's kind of the, plus, you know, as a good faculty member, part of my job is to make sure that I torture the students. So that's kind of the other element of the first assignment. So anyway, so that's all I have for today. I assume this time is working for you. So the 10 to 11, the back-to-back lectures are okay. And then tomorrow we're back at 1. And then on Thursday, we're going to be at 11 again. Now, I will also be in preparation. Now, Thursday, we're going to start doing the computer thing. There are a few extra little things that need to be done. I have a video for that. I'll post a video so you can kind of do a little look ahead for that. I'll post a link to that in the, where will that be? That will be on, let me share the screen. It's not there now yet, but that will be, we notice in the lessons, there was a one called Implementing Discrete Event Simulation Models in SimKit. Currently, it doesn't have anything in it, but that's where I'll put some links that have to do with doing them on the computer. So I guess one of the advantages of having everything in one big blob last time is that everything was right there. The disadvantage, it was kind of hard to see the forest for the trees. Here, hopefully you can kind of see the structure of things in the different modules. And so you're gonna have to kind of look in different places for stuff. So that'll be there. But that is it for today. And if there are no further questions or comments, I will see you tomorrow.